Morning, everyone. Helge Bastian. I'm the general manager of synthetic biology at ThermoFisher Scientific. What can I say? I really am excited to be here again, second year, right? And listen to all the talks. I wonder why we haven't started earlier, right? So, and all the talks have alluded to what was discussed yesterday too. Is it a good idea to do it, or are there any concerns needed to kind of reconsider the activity? And it looks like that we all have good intention, and that exactly is going along with the mission of ThermoFisher Scientific, which is enable our customers to make the world healthier, cleaner, and safer, right? I'm a little jealous to what I just heard from Emily again, 160 million or what it was. That is pretty close to what you see almost Thermo Fisher's R&D budget is for the whole company. So we are not a startup anymore. It's an $18 billion company, and we spend a significant amount of money in product development and new technology development. But for a startup in this very area of 160 million in funding, that is a really good number, right? So I just want to say also that beside us being part of a large corporation, we are specifically funded also in a subsegment of the company. We belong to a group, it's called Biosciences, that is the innovative product development team within Thermo Fisher. And what we do, we are involved in also, like most of us here, in engineering nucleic acids. So if you specifically say, what are we doing really in synthetic biology? We really do engineer nucleic acids in outside of the cell and inside of the cell too, through genome editing technologies, right? So what I'm going to highlight today is just the things that are circled. I want to talk a little bit about what our approach is to high precision editing. And this will also allude to the fact that a technology that people maybe have dismissed for some time, the TALEN factors, might have a good application when it comes to high precision genome editing. And then I also want to just give you an update on what has been reported last year on our high throughput technology platform for oligosynthesis. So as I mentioned, the technologies that people use for genome editing is CRISPR and TALEN factors. And we're going to talk in a minute about why TALEN factors may have an advantage in high precision editing. And then again, the way we look at engineering nucleic acid is we have vertically integrated all the building blocks to get to larger genes, right? All the way from amidites up to genes, to pathways, and hopefully then to chromosomes is what we have under one roof with an expert team in all categories, and hopefully this will help our customers also to achieve their objectives. So if we look at and compare the TALEN factors and the CRISPRs, there's two, of course, main differences. And the one, most importantly for this subject here, is that the PAM dependence. TALEN factors have no PAM dependence. There's no restrictions as far as sequence specificity, so you can design any TAL. And what we have figured, as we see in a bit, is that when it comes to homologous-directed recombination, we see that the TALEN factors show better results than the PAMs. But the biggest challenge essentially is what we call the PAM or CRISPR desert. So because there's, of course, parts in the genome that don't have PAM sequences, and there's a lot of single point mutations where you want to make an edit. So how to overcome this? And this is exactly where we thought, let's have a look back to the technology and see how it performs, because the next generation of TALEN factors, the so-called TLS TALs, can attack essentially any sequence in the genome. And that's exactly what we did. So you design TALs, especially in areas where you can't have a chance to use the CRISPR technology. And as we probably most of us know, the closer you are to the point of edit, the better it is. And you can design the TALs accordingly. So therefore, what we found in comparison is that, first of all, if you have no PAM site close to the editing site, then of course you have little choice. but also the experiment itself shows that you get much better homologous recombination. I just want to say the edit if you use the telefactors, right? So many more data on this, and also if you compare sites where there is a PAM sequence, we saw better results with the telefactors, and we believe that the homologous recombination, the way the site is cut will support the introduction of what we only need is a small oligo. So a few more data, but I think we don't have time to go into this. So a brief update on our platform that we had shown about a year ago. So this is what we call the 3D microchip. It's a 34,000 well microchip where we do 34,000 oligos, 35,000 oligos at a time. And this is our new platform to really go into gene synthesis with. We have, as the new development, you will see it's a really small chip. It will replace all the 96 well manufacturing machines that we have. And we have started to implement this and transfer this into manufacturing. So the core that we have today essentially is that, I think you see it on the last two bullet points. The core we have is if there is interest for high throughput users, not to use gene synthesis as a service that we provide for 17 years, but also want to collaborate with us or even want to use this technology in-house. That's where we'd like you to talk to you about. And as an overall take-home message for today, there's really four big points I want to bring across. First one is when it comes to the expertise along the whole what we call value chain, from building blocks, amidites to genes, and also editing the DNA in the cell. This is what we have under one roof. What I'd like you to consider, as I just said, is the new technology, and you can talk to us because it's not commercially available at this point in time. We will have a new technology also in the CRISPR area, so there will be new enzymes coming along, and we run an early access program for this. So here again, please reach out to us to participate in that. And last but not least, if you are interested in high precision editing of the genome, consider TALENs, because TALENs can go where CRISPRs can't. And this is where we can close. Thank you. Any question? Yes, one.
How often do these CRISPR deserts?
Well, we haven't fully finished this. It could be somewhere of 30% of the genome that doesn't have PAM sites. Let's assume they need a PAM site. Of course, there's different CRISPRs where you can use different PAMs. But you don't have this issue with TALENs. And TALENs do work really well. I think when the CRISPR came along, people were a little bit afraid about the cost of the TALENs. And I showed them one of the slides, but in the interest of time, I couldn't really get into the details. But you get TALENs these days because we have optimized the manufacturing process. Today, you get TALENs at the same pricing level as you get CRISPRs. So that is not the issue. Turnaround time for making TALENs, we have a high throughput TALEN manufacturing platform now, is also possible. So we use both technologies, right? And of course, it would be nonsense to say TALENs comes back and replaces CRISPR. That's not the case. But there's applications where you are dependent on a PAM sequence and you want to edit where telefactors are really valuable tools. So for those that ever thought, it's the name of the game is CRISPR these days, that's not exactly true. TALENs are really relevant genome editing tools, right? So we're happy to provide that.
And what about the efficiency between?
We see you can have perfect efficiencies with CRISPR, but we see the same excellent efficiencies with telefactors. We do mRNA with telefactors. When we do CRISPR, we do the RNPs, right? And efficiencies are extremely high for both technologies these days. And I mean, this is, I think, if you look back the last 3 years or so, was tremendous, acceleration of to make it more efficient, going from plasmid to mRNA to proteins, and that's what you see with telefactors too. Okay, thank you very much.